In this video, I'll use decision tree as a context or vehicle to explain the difference between absolute deviation and variance, hopefully giving you some intuition behind the difference between the two of them. So let's say that we have the following two decision trees. We have one right here, A, and one right here, B. And in the first decision tree, let's say that this part right here, this is called the parent node. We have two classes, and they're of equal amount, 400 of class 1, 400 of class 2, and we do a split resulting in two child nodes. So for the first child node, we have 300 of class 1, 100 of class 2, and then for second child node, we have 100 of class 1, 300 of class 2. In the second decision tree, we have the same starting point of the parent node, and when we do the resulting split, we have 200 from class 1, 400 from class 2, 200 from class 1, and 0 of class 2. Okay, so how would we evaluate what's called the error of these decision trees? Well, one thing that we could do is we could use something called the misclassification rate. And that is, misclassification rate is defined by the following formula. Let's see here, let's grab the pen. Misclassification rate. Is equal to 1 minus the max of the probability of J given T. Okay, so what does this mean? Let's call this misclassification rate at node T. So it's for a given node. For a given node, we're looking at what's the majority class. This is what the max means. The J represents the classes that are available under discussion. So in our case, we're talking about two classes right here. So we could have, so J is going to be 1 or 2, for example. So this is saying that go into a node and look at what's the majority class and represent that as a fraction. Subtract it from 1, and that'll be your what's called the misclassification rate. And this implicitly assumes that the majority class for a given node is the correct class, quote unquote. And anything that's left over, that's the thing that's not correct, or that's dirtying the node, so to speak. So let's just do that for this tree right here. So we'll do the parent node. So let's see here, what would we have? We would have, let's call this error, or I'm going to use error, the same thing as this classification rate. So error of, let's call this the parent of A. So we're talking about this guy right here. Is equal to 1 minus. So both classes are the majority class, so to speak, so we can pick either one of them. Let's say that for we use class 1, so it'll be 400 divided by the total amount, so that's 800. So then this fraction right here will be 0.5. So then the error rate is 0.5. Okay. Now how about the children node? So the children node we have, let's see here, we'll write this as error of, let's see, C of A, C1, let's say, the child 1. Let's write this meter. Child 1 is equal to 1 minus, well, what's the majority class in this case right here? Well, that's class 1. And what fraction does that class make up of the total for that node? So that's 300 divided by 400. So that's 0.75. So that's 0.25. And then the error of the second child node. So that's right here. Now this is the class 2 would be the majority class. So that will be the same thing. It'll be 1 minus 300 divided by 400. That'll be 0.75. Okay. Now, then in order to calculate how much did our error improve from doing the split, we would need to do a weighted average based off of how many items, based off of the amount of objects that got funneled into each of the node. So the weight would be the weighted average error of the children node would be, well, so let's look at this guy right here. Out of 800 things that we initially started with, 400 came into this node. So that will be its weight, 400 divided by 800. Times. What was the error on this node? We said it was 0.25 right here. Okay. Plus, and then we started with 800 and 400 came into this node, so it's the same weight. Oops. Yes. Times 0.25. So it's a half times 0.25 plus a half times 0.25, so you'll end up with 0.25. Okay. Now let's look at this decision tree right here. What's the error of this decision tree if we were to use the error rate specified by this formula right here? So same thing. Let's start with the parent node. It'll be error of P of B is equal to 1 minus, so we had the same starting point, so it's going to be the same thing, 1 minus 0.5. Okay. Now how about the children node? Error of the P of the C1 minus of dash B is equal to 1 minus. All right, let's take a look at the majority class. So majority class in this case is 400, and the fraction that this majority class makes up of the total for this node is 400 divided by 600. So it's 4 divided by 6. So that's going to be 2/3 minus 1, so that's going to be 1/3. Okay, how about the error of the other node? 1 minus, let's take a look. What's the majority class? So it's 200 right here. So 200 out of 200, that's going to be 1. So that's going to be 200 divided by 200. So that's going to be 1. 1 minus 1, that's going to be 0. Okay. So then if we do the same calculation, let's find the weighted error and see what that is for the children node. So let's call this the weighted error of B to distinguish it from the other tree. Weighted error of B. So then, let's see here. So we started with 800 right here, and then we have 600 right here, so that's going to be the weight, 600 divided by 800. Times, what was that error? It was 1/3. Plus, so we have a total of 800, total of 800, so then this has to be 200 divided by 800 times, what was this error? This was 0. Okay, so then if we do the math, this is the same as 6/8 times 1/3. This here. So that's what? So it's going to be 2. So that's going to be 1/4. Notice that, or this is going to be 0.25. Oh, okay. So this weighted error of B is 0.25 right here. And the weighted error of A is also 0.25. But it seems like that. Um, it seems like that doesn't feel right, because what do we have for B that we don't have for A? We actually have this node right here, where we only have a what's called a peer node. We only have one class for a given node, and we don't have anything else in this node. Only one class, and we would like our error rate to reflect that we would prefer a tree where we have a pure node versus a tree that doesn't have a pure node. And it seems like this misclassification rate, if we are using this formula, it won't be able to distinguish between these two trees to say that this should have a smaller error rate than this one. So I'm going to pause the video right here because I think it's already gone long enough. I'll go into the part 2 to explain what error rate we should be using that could help incorporate this information, the information that we want the error to to prefer a tree that results in a pure node versus one that doesn't. So I'll see you in the next video.